So, Chapter 8, we will introduce you to the quantum mechanical model of the atom. There was a big change in philosophy that happened right before, as quantum mechanics was being discovered and learned about. So, it was believed at some point in time that physics could figure everything out. And once we figured out where everything was and where everything was going, then essentially there'd be like this loss of free will. Like, all right, well, we know what's going to happen for the rest of the world, and everything's will be figured out. And of course, with quantum mechanics, when we found out that you can only understand where things are and where things are going to a certain degree, when there's uncertainty, then that all ended. So, although many people still do believe in fate and that things have already been pre-written of sorts, but much of that has been disproven, if you will, on a scientific level. And this was a big debate. And of course, while I'm doing this video in the United States of America, Einstein, he's one of our most famous scientists. He's originally from Germany, but he's always been very popular in the United States. He was not very popular in Germany. He was not very popular in England, but he's always been popular here in the United States. So the Germans saw him as a Jew, and the British saw him as the German that was trying to disprove Isaac Newton. So, and there's many other: Niels Bohr, de Broglie, Planck, Heisenberg, Dirac, Schrodinger. Schrodinger, actually, if any of these that I want to meet personally, I'd probably be Schrodinger. He's just he seems like a really interesting person on an individual basis. So, but with the quantum mechanical model, it explains many things. It's the reason why we have the periodic table the way set up with electronic structure. And the following chapter, we will talk more about the periodic trends. Also talks about it explains chemical bonding. And although this is an intro class, bonding is much, much more complicated. We do talk about the octet rule quite a bit, but there are other rules and other bondings happen as well. And the practical part of quantum mechanics led us for the basis for things like lasers and computers and many, many other things, the high technology that we enjoy today. So, in quantum behavior, it's only really noticeable for very small things. So I myself have a wave function, but I'm too big, and it's not. Although I am a relatively large human being, things that are maybe above 10,000 atoms. It's really hard to find the quantum mechanical properties of something like that. So I'm way too big, and really, chemistry is the study of matter, but much of chemistry really looks at the electrons. We do have nuclear chemistry, and the nucleus is much involved, but really the nucleus mostly involves interaction between the electron cloud and the nucleus, and the electrons, at least for most of the chemistry we look at, is really what it's all about. And with electrons, I've mentioned this before a little bit, that electrons are smaller than atoms, of course, but I guess electrons, well, they can, in a particle accelerator, electrons can get really flat. They're almost like pancakes. And they can be really long. But directly observing one using light, that's impossible. Among other things, the light is going to interact with the electrons, so you're not really seeing it. You can kind of image electrons, at least electron clouds and atoms, by various techniques, but it's not something you can see using visible light. So the quantum mechanical model, explains many things, and to give you we won't necessarily go into this chapter, but subsequent chapters, certain things like why elements are metals and why are they non-metals, so why do they form. It's about bonding, and also like whether or not electrons get removed or added to the electron clouds, And also, some elements are extremely reactive. Fluorine, for instance, is very reactive. The alkali metals are very reactive. All the noble gases are very unreactive, and certain metals like gold and platinum are very unreactive. So it's interesting. So and it and we can predict properties, and we actually use this to predict some of the properties of the super heavy elements, and uh, that really well, we also can directly probe them now. But I mean, some of the elements are just they're not even around long enough to be able to do certain experiments with them. So before we get into the quantum mechanical model, let's talk about electromagnetic radiation. And what is electromagnetic radiation? It's essentially it's a carrier of the electrostatic force. So four fundamental forces: gravity, electrostatic, nuclear strong, nuclear weak. Some places say five forces if they include dark energy. Some say three because electrostatic and nuclear weak are the same thing. But that's what a photon does. And light is a form of electromagnetic radiation, and essentially, if you want to go with the most basic, it causes charges to oscillate. So that is the simplest way to look at it. And photons and electromagnetic radiation, what they have oscillating, they're transverse waves, meaning the displacement is perpendicular to the motion. So if the wave is moving forward, the electronic field is oscillating up and down, perpendicular to the motion, and then perpendicular to both the motion and the electronic field is the magnetic field moving up and down. And since there's three dimensions, the electronic field and the magnetic field can both be perpendicular to each other and the motion. I'll show you a picture soon. And then electromagnetic radiation moves at the speed of light, which is pretty fast, 3 times 10 to the 8 meters per second. So here's the picture showing the direction of the flow, and this is a transverse wave. And so sound is a wave. Sound is a longitudinal wave where the displacement of the particles that the sound travels through is parallel to the direction of travel. But the displacement here for light and other electromagnetic radiation, the electronic and magnetic fields move perpendicular to the direction of travel and to each other. And I already mentioned sound. Sound is a longitudinal wave, but compared to light, its sound is very, very slow. At least in sound, 340 meters per second. That's in normal air. The more dense the material, sound will go faster. And so this is just wave properties. Amplitude is how high the wave is, and then the wavelength is how from you can go from crest to crest, trough to trough, or the start to the finish. It's just how long the wave is. So, and these are important when we talk about light and other forms of electromagnetic radiation because it changes the properties of them and also how they interact with matter. So here is a wave. How high the wave is the amplitude, and the wavelength. This is like I said, it's just how long the wave is, and when it starts to repeat itself. So it really just depends. You can do it from trough to trough, from peak to peak, or from the start to the finish, however you want to look at it that way. And frequency, just definition of frequency. This just means the number of times that something happens. So I mean, you can use frequency not just for it's not exclusive to light. You can what's your frequency for eating meals? Frequency for me, I usually eat breakfast, lunch, usually a snack around 4 o'clock in the afternoon, and then dinner around 6. So my frequency of eating is about 4 times per day. Depends on the day, of course, right? So, but that's a frequency. It's just how many times stuff happens over a period of time. And for frequency in terms of light, it's the number of waves. And these are interacted. I'll talk about later that frequency and wavelength also characterize how the radiation, what effects it has, and also its energy. So just basic things, basic physics. the speed of a wave is the frequency times the wavelength. It's how long the wavelength is and how often it occurs. So that equals speed. In this case, the speed of light is the frequency times the wavelength. So, and with interesting thing with light is and electromagnetic radiation, there is a speed limit, it seems, to the universe, and it's the speed of light. And the speed of light, it's, well, I mean, like I said, it doesn't change. And maybe you've heard of relativity and how time is not constant. Well, the speed of light is constant. Speed is distance divided by time. So speed is in like miles or kilometers per hour. That's distance divided by time. So speed of light is 3 times 10 to the 8th meters per second. If the speed of light doesn't change, what happens when things are moving? Well, depending on your velocity, your time changes. So it's no longer, that's the interesting part about speed of light. Speed of light cannot be broken, but what changes is your time, the way that time works. And that's an interesting part of that, but that's for future classes. But I like talking about it because I think it's cool. So amplitude and wavelength, so different colors. So red light has, and red light's on the top here if you can't see colors as well, and then there's blue at the bottom, yellow in the middle. Red light has the longest wavelength at about 700 nanometers, and violet has the shortest wavelength of about 400 nanometers. And then, so that's different wavelengths, and they have different colors. And then shown on the right here in green, there's dim light and then bright light. You can see the bright light has a higher amplitude. So a higher amplitude just means more light. And so the other thing to notice, we'll talk about later, the higher the frequency, the more energy. So just looking at the image on the left, so if you're going to be in the ocean and there's a storm, which storm is a more powerful storm? And the answer is the one on the bottom, the lambda sub c. And the lambda, that upside down y, that's the lowercase lambda. That means wavelength. And so the bottom wave has the highest energy. So the higher the frequency, the higher the energy of the radiation. So what color is, so we as humans, we can perceive visible light. Some people can see a little bit in the ultraviolet. I can to about 380 nanometers. It looks kind of like a really light lavender-ish color to me. There's some ideas that certain painters like Renoir, he had some cataract surgery, and many people that have cataracts removed can see a little bit further in the ultraviolet after that. And most humans can see near infrared. It's pretty easy to see 800 nanometers. Well, it's really dim. It looks like to me, it's like a dark brick red. It's like a really blackish red color is 800 nanometer light. Well, the problem is we as humans can't see it very well. We as humans, we see green the best. Green is the brightest color of all the colors. And our eyes, we have 3 different types of light sensitivity. We have red, blue, and green sensitivity, and just the intensity of that brings to our brains. Our brains interprets that as color. So we are not spectrometers. We're not spectrometers, but we can perceive different types of light, and we tell it by the different intensity of 3 different sensors to our brains. Whereas spectrometers, they are much better than the human eyes. Although humans have really good sight compared to everyone else in the animal kingdom, but we're not nearly as good as spectrometers. And white light, the different thing with white light is all colors. And you can split white light up. So in this prism, you have white light coming in, and it splits into different colors. And also, so if you like the woman in the picture here is wearing a red shirt, that means that the light coming in, it's absorbed except for the red wavelengths, which are reflected, and that's what you see. We as humans will perceive that as red. So let's see here. Which statement describes the difference between a bright green laser and a dim red lasers? The two lasers the two lasers emit light from the same frequency. Well, that's already wrong because different colors are different frequencies. B, the two lasers emit light from different frequencies, and the light from the green laser is smaller amplitude. Or C, the two lasers emit light of different frequencies, and the light from the green laser is a greater amplitude. The answer is C. Although there is a parlor trick where you take, I have a 5 milliwatt laser, well, at least I did before they broke, and there is a 5 milliwatt green laser and a 5 milliwatt red laser, and the green looks a lot brighter, but that's just because humans see green better. So this could be wrong, but I mean that's kind of this is I think you get the idea that the higher frequency, I'm sorry, the higher amplitude is the more intensity. Although since we're humans, we can actually perceive green brighter than we do red. And visible light, so we can only see a small part of the electromagnetic spectrum. And we'll talk about the whole electromagnetic spectrum. And the shorter wavelength, high frequency light, these have high energy. So radio waves, microwaves, these have the lower energies. Gamma rays have the highest energy. And there's even further is cosmic radiation is even higher. And anything beyond visible light is known as ionizing radiation. And what does ionizing radiation do? It creates ions. How does it create ions? It rips electrons off. So it can really damage things, is ionizing radiation. So here's electromagnetic spectrum. And if you look on the far left, you have radio waves. Radio waves, then microwaves, then infrared, then ultraviolet, then X-rays, then gamma rays. So what do all of these do? So radio waves, what radio waves do to matter is they change the orientation of the magnetic moments of nuclei. And so we use radio waves for various things. We use them for telecommunications, but also we use the effect it has on the nucleus for nuclear magnetic resonance imaging, also known as MRIs. It used to be called nuclear magnetic resonance imaging, and people were afraid of the word nuclear. So what do? They called it magnetic resonance imaging. So, but of course, magnetic resonance imaging, MRIs, are extremely safe. They're very, very safe. They cannot harm you. I mean, if you're claustrophobic, they're not a lot of fun. I've had 3 of them in my lifetime, and I say they're very safe. They're kind of loud, but in them you'll hear like a brrr, you hear a scanning sound. What they're doing is they're looking for your hydrogen atoms, and they're finding your hydrogen atoms, and then they give you a 3-dimensional slice of your body, and you're imaging where your hydrogen atoms are, and then from that they can tell what type of tissue there is, if there's ligaments, if it's muscle, if it's blood, if it's bone, for instance. And then they can look for things like if you have a disc injury, like I've had for MRIs before, or like sprains and various things. So, or different things growing in your body that shouldn't be there. So that's what we use MRIs for. So microwaves, what microwaves do is they cause molecules to rotate. So a water molecule is kind of shaped like a V. A microwave oven works by making the water start to spin, and then that's rotational energy. Then when the spinning water molecules hit other water molecules, then that spinning energy is transferred into translational energy, and translational energy is temperature. So that's how microwave ovens work. And the microwave oven was originally found by someone working at a radar station, and the individual had some chocolate bars in his pocket, and they kept on melting, and they figured out it was the microwaves coming from the radar station. Radar uses microwaves, and then from that led to the formation of a microwave oven. So it was actually an accidental discovery. Infrared. what infrared light does. Also, we depends on the people. The younger scientists call light infrared, visible, and ultraviolet. Some of the older scientists only call visible light a light, but I call infrared light. It's the newer hip trend in science. So infrared light. So infrared, besides that, means less than red, so lower in energy than red. Infrared light causes molecules to vibrate, and also energy coming off of like fire. So if you have energy from radiation, so you put your hands over a fire to warm them, it's the infrared light coming from the fire is what's warming you up. And that light hits the molecules in your hand, and that causes the molecules to vibrate, and then by molecular collision increases the temperature. So same idea, infrared light. And your eyes we actually will focus the near infrared to visible. So infrared light can be dangerous to your eyes, like for a laser, because your eyes will focus it, and you can burn yourself. I was a laser spectroscopist in graduate school and postdoc. So, and the infrared light, it's invisible, you can't see it, and it's also your eyes focus it. So it's very dangerous to work with. And then visible lights. So I'm depends on the person. I mean, most humans can see 800 nanometers, and it looks like a really dark brick red, like a Ti sapphire laser shoots out 800 nanometers, and most people can see it. And most people see to about 400 nanometers. After that, it's hard to see the visible light, but the rest of the colors are in between. And like I said, we humans, we only see three colors, truthfully, and then our brains just we perceive the colors just based off of the different intensities. And I mean, there's other animals that have other types of photosensitive cells. Well, humans, most people have three. Some people have two or one. Some people have four. They're known as tetrachromes. But our brains don't really have the power to perceive light and colors beyond what someone with three cones have. So it's not a huge advantage to a human to be a tetrachrome. So beyond violet is ultraviolet, and I didn't mention what visible light does. Visible light causes electrons to jump up and down their energy levels. Ultraviolet light causes big jumps in energy levels of electrons. It also can ionize the outermost electrons. So all the ionize mean has enough energy to rip off electrons from an atom. And why is this important? Because this will cause chemical bonds to be broken, and chemical bonds being broken means damage. So ultraviolet radiation can damage chemical bonds, and as such can damage cells and other things. So ultraviolet light tends not to damage metals as much. X-rays do, though. So moving on to X-rays. X-rays, they work well. They ionize surface electrons, but they can also go deeper into the core of the atom, so that the lower level electrons can be ripped off by X-rays. So X-rays are more damaging than ultraviolet light. So ultraviolet light, though, let me move backwards. In the near ultraviolet, we have the ranges UVA, UVB, and UVC. Beyond UVC, the atmosphere just absorbs it. And UVA is the primary cause of wrinkles, because UVA too much radiation exposure can scar the dermal layers of your skin, and then the folds over the dermal layers of your skin are your wrinkles. And UVA was the most common cause of wrinkles. I mean, you can get wrinkles from you can be born with them. You can also, just by repetitive motion, can cause a wrinkle. But when you see sunscreens say anti-aging, it means it blocks UVA. UVB is what causes sunburn, suntans, and carcinomas, melanomas. But we as humans, we're also slightly photosynthetic, where we take UVB radiation and we can turn cholesterol into provitamin D3, so calciferol. So we are actually photosynthetic, much like plants, although we don't get uh, sunlight is not our primary food source, so we don't necessarily photosynthesize food to eat, but we do photosynthesize uh, uh, the precursors to vitamins, specifically vitamin D, which our liver can then turn into vitamin D, and we use it to help with our bones. So we are slightly photosynthetic. Huh. Fun fact of the day. X-rays, I mentioned before, they're more dangerous. X-rays can also cause skin cancer. So dentists used to stick the fingers in the patient's mouths and then take the X-rays. Of course, dentists started having really manky-looking hands from all the exposure to the X-rays, and I mean, maybe some of the reasons why people are afraid of dentists. I don't know, but ultraviolet can only really cause skin cancers. X-rays though can cause other types of cancers because it'll penetrate further, but it can still cause skin cancer. Gamma rays. So gamma rays deal with energy transitions in nuclei. So just like electrons have wave functions we'll talk about and jump up and down in energy, protons and neutrons do too. And gamma rays deal with that range. Gamma rays are also released during nuclear reactions. So, any nuclear event, so radioactive decay, nuclear fission, nuclear fusion, gamma rays are produced. And these are the highest energy, and they're really hard to stop. So ultraviolet light you can block with clothing or some sunscreen. X-rays you need, so you can do it with a really thin layer of lead, or I mean, you could do it with clothes, but you'd need thicker clothes. I mean, just distance and like a block of wood could block some X-rays. Gamma rays, though, you need like a foot of lead or a couple meters of concrete, so they're a lot harder to contain. So they're just really high energy. And even beyond gamma rays, you can have cosmic rays. What these do, they're released from various events in space that we don't really quite understand, but we see them, and they're just really high energy photons. So I mentioned before we are talking about spectrometers. White light is actually all colors. So light's different than pigmentation. So if you take red, green, and blue, well, the way that we perceive it, if you take all the colors and you throw them together in like a paint set, you get kind of a grayish brown looking color. Whereas with light, if you throw all light together, it's white, or we would perceive it as white. If you took red, blue, and green light and put it together, we humans would perceive it as white, although it wouldn't be white. But white light is all colors, and you can break it apart. And this is infrared light, but you can image it. And this is a false image. It's so that we as humans can perceive it as the different colors, for the different temperatures. So another conceptual connection here. Arrange the following types of radiation in order of increasing wavelength: visible, X-ray, infrared. So the shortest wavelength is the highest frequency. That's X-ray. X-ray is the lowest. Then it's going to be visible. Then infrared. So that's the increasing level. So we can use high energy radiation to kill cancer cells, and this is one of the radiation treatments you can do. And there's more ways of doing it than just than using machines with beams of radiation. You can also inject radiation into people, and cancer cells they grow faster than the other areas, so they're kind of greedy, and so from that it tends to be relatively easy to get medicines to cancer cells. Of course, with chemotherapy, there are other cells that are kind of greedy. Things like hair follicles and stomach lining, those tend to be they use up a lot of resources, and so one of the side effects of chemotherapy oftentimes is the damage to those areas as well. but you can use beams of radiation to hit a high dose in a certain area, and just certain areas are just more responsive to various types of radionuclides. So iodine, for instance, can be used to hit your thyroid, and it'll really just hit your thyroid and not the rest of your body. So let's talk about some more properties of waves. There's interference, the interaction between different waves, constructive interference and destructive interference. Constructive interference causes things to interact so that they increase in amplitude, and that's called in phase. Destructive causes amplitudes to decrease, and that's called out of phase. So waves in phase, where the peaks are where the peaks are and valleys are where the valleys are, this increases the amplitude of the wave, and this is a constructive interference. Out of phase, where there's a peak, there's a valley, and vice versa. This causes destructive interference, and the waves cancel out. Of course, there's usually much more of a complicated pattern from this. Diffraction, this is a property of waves, not particles. Particles don't do this. But when there's an object, the waves tend to bend around it, so it's kind of I'll look at some pictures later. It's hard to describe using just words only. And then you get the two-slit experiment will show, and we'll have an interference pattern. The interference pattern is where there's constructive and destructive interference. So, and this is for all light waves. This is for all waves. It's not even just light and or electromagnetic radiation. It's all waves. Ocean waves do this too. So here is wave diffraction. So imagine instead of using light, imagine we have waves crashing at a wave break, and then there's a hole in the wall, and then this is what the waves look like coming out through that hole in the wall. So that's even just an ocean transverse wave, and light waves are the same thing. So let's say instead of waves, you're hitting golf balls at a hole in the wall. What's going to happen? Well, golf balls are going to hit the wall, and the ones that go through, right? So this is different than a wave, where the waves will kind of bend through that barrier, whereas particles do not behave that way. So the two-slit experiment, we'll talk about this when we talk about the wave-particle duality of electrons. And if you have a light source and you have two waves interacting, they will diffract through the two holes. And then you will have constructive and destructive interference, where you'll have areas of high intensity and areas of low intensity, but then you'll also have the in-between states. And that's from the interference of the two waves coming through. So this is actually where Einstein got his Nobel Prize. So, but this also helped to explain that the idea of the quantum world. So, like I said, Einstein was not very popular. He was very unpopular in Europe, at least, where we in the United States, we always loved him, took him in with open arms. But relativity is not. Although we know him for relativity, relativity was a big point of argument in Europe at the time, but the photoelectric effect, this is what got him the Nobel Prize, like I said. And the photoelectric effect is if you have light and you shine it at a metal surface, nothing happens to a certain point. After a certain point, the light will start to generate electrons. And once you generate electrons, if you add more light, more electrons are generated. If you increase the frequency or energy of the light, then electrons come off, but with faster energy, faster kinetic energy. So what Einstein did is he used this then to predict that, or to describe the idea of the quantum world. And the idea where things only exist in certain packets of existence. So, and photons are one of them. It's all discrete mathematics. So, like maybe you've heard of something called Zeno's paradox. Zeno's paradox is if I take half a step to the wall, and then or half the distance to the wall, and then I take half that distance, then I will never reach the wall. Now, the problem with that is, Zeno's paradox is that space-time, so Einstein talks about space-time. Space-time itself is quantized. So we get to a certain point where things actually will touch because you can't go half a quanta of space-time, and that's known as the Planck length. So we actually can never determine what that is because we're existing in the universe that it exists in. We can get to a point where we can't go any further, but that's not necessarily proving it. So that's another thing this is something that's in a way it's impossible to prove. So this is interesting. So this is the photoelectric effect, and like I said, that light goes in, and electrons are ejected from the metal surface. Well, if the light is too low in energy, nothing happens. Gets to a certain point, electrons start coming off, and then they can look at the energy of the light, or the energy of the electrons coming off is the by time of flight. So the faster electrons will get there. We'll get there faster, and then if you increase the light, the energy of the light after that, the energy being, I mean, the frequency, then the electrons come off faster. And if you increase the amplitude or intensity of the light, more electrons come off. So it tells you that electrons are discrete, and also light is discrete. So, but okay, so what is this also? This means that there's a threshold, that the frequency of light or the energy of the light, once it reaches a certain point, it has enough energy to rip electrons off, and that energy to rip electrons off, we call that the binding energy. We'll get to that soon, but then this also talks about what photons are. So there's actually little tiny energy packets that light exists on. These are photons. So in a way, light actually has a particle-like behavior because it acts like a packet of something, and you call this the quanta, and that means that the universe is based off of these quanta, which also makes sense though, that the universe is not as discrete because space has structure. If you have an infinite number of states between two things, you could never get anywhere, and that allows the universe to have structure. So the fact that it doesn't take forever to get from point A to point B, that means actually that the universe is finite, and there are a certain set quanta of existences. So there's a real, that looking back, of course, that's an obvious the obvious explanation. But of course, for Einstein, in the time, this was a big deal. So and we came up with the equation from this, that the energy of a photon is Planck's constant times the frequency. Also, the frequency is speed of light divided by the wavelength. So it can be hc over lambda. Lambda speed of light, or I'm sorry, lambda is the wavelength. C is the speed of light. It could be h times. We usually use nu. Looks like a little v for frequency. So the energy of the photon, that's the hc over lambda. The v is nu. I don't know why we use the Greek letter. That's lowercase nu. And the at the threshold, the binding energy. This is how much energy the electron is held to. So if you give the electron enough energy, it will fly off of that atom, and that is the binding energy. And if there's extra energy, then if the energy of the photon is greater than the binding energy, then that extra energy will be ejected in the form of kinetic energy from the electron. So let's look at this. We shine light on 3 different wavelengths, 325, 455, and 632 nanometers on a metal surface, and record the observations for each wavelength. So no photoelectrons were observed. Photoelectrons with a kinetic energy of 155 kilojoules per mole were observed. Photoelectrons with a kinetic energy of 51 kilojoules per mole were observed. Wipp's observation corresponds to 325 nanometer light. So no photoelectrons observed. This is the lowest energy. That's going to be 632. So 455. That's the medium one, and the medium one's going to be the lower kinetic energy one. So that's part C, and the photoelectrons, and 325 nanometers is the highest frequency, highest energy. That's going to be observation B. So, right there. Atomic spectroscopy and the Bohr model. So, Bohr came up with the idea of, and you maybe seen Bohr model quite a bit. It's the idea of the orbits that an atom has electrons orbiting it. But Bohr took the spectra of atoms and ions and went ahead and took it a little further, and they noticed certain things. So when you excite atoms or ions up, they can emit something called an emission spectrum, and it's unique to each atom, ion, or molecule, as we'll find out later. And it's like a fingerprint. It's unique to it. So because of the emission spectra, you can use it to identify things. And flame tests are very common. Atomic absorption, AA tests. These can be used to determine. It's really easy to determine how much stuff is in something. So, for instance, if you go to the hospital and if you have a heart issue, they'll draw your blood and throw it into an atomic absorption machine, and it'll tell you your relative amounts of potassium and sodium ions, and that's real easy to find using atomic absorption. That's based off the emission spectrum of your blood. So that's an example of that. So if you look here, we have a picture showing the different noble gases, and they're different colors. And if you've ever gone to a place like Las Vegas, you can see they call them the neon lights, but neon light is only the red one. The different colors come from the things. Also, oxygen is a white one, so there's also molecules you can put in here. Molecules have spectra too. And really what's going on is our eyes just perceive these colors. Also fireworks, the different firework colors, they're from different elements, or well, salts. So the pink one is from lithium, and the yellow one is from sodium, for instance. And they have characteristic lights. And if you've been to I love firework shows. If you've been to firework shows, you start seeing the same colors over and over again. But I'm still amused. I still like watching fireworks. But I mean, you'll notice that there's different colors. And even this picture here, I can see pink, and I can also see a red. The red's from strontium, for instance. So just like with the white light, you can take the white light, and throw it through a prism, and you can break it into different components. You can take light coming from something like a hydrogen lamp, and then you can split it up into the individual spectral lines, the colors. And this is the spectra. So you can see here's helium and here's barium. White light on the bottom, it's all colors. But the helium and barium, you can clearly tell that one is different than the other, and it's really easy to see that you can tell something is helium or not helium really fast from one of these. So this is what it means by that. You can find out what's in something by the different amounts of light coming from something, and also relative amounts. So you can identify elements, and these are actually going to be ions in flame tests. And if you can't see the colors, sodium on the left is kind of it looks kind of orange here. It's kind of a bright yellow orange, kind of the way I perceive it. Potassium is a lavender color to my eyes. Lithium, not shown here. It's more of a hot pink to my eyes, a fuchsia color. And barium looks a little greener than this picture. But it's also, like I said, used in fireworks. And another scientist, Rydberg, Johannes Rydberg, I call him Rydberg, and he noticed that the lines of the hydrogen atom coming off the spectra have this certain value. The inverse of the wavelength is equal to what's called the Rydberg constant, and then the difference between two different integers. So just listed as 1 over the square of two different integers, m and n, in his equation. Bohr came along, and Rydberg you start to see this idea of the quanta, these individual numbers, but doesn't explain why they're stable. And neither did the previous models. The nuclear model from Rutherford, he didn't explain some of the chemical properties. So Bohr went along and said, hey, he came up with the idea of the orbits of electrons, and then also talked about the stability of them and how they bond. So, of course, Bohr brought some of the ideas and brought in the quantization of things. And so there were arguments with Bohr. I said if there were actually orbits of electrons around the atom, the electrons would slowly lose energy and would be emitting radiation the whole time they were losing energy as they came down to the nucleus. And they eventually would come to the nucleus. And then he came with the idea that they were fixed. So we sat here for a while, and Bohr model is a very powerful model, and it's still taught today. And the reason why they have the stationary states, like I said, because otherwise the electrons would lose energy and be emitting radiation the whole time that they were there. And also the idea of Bohr's model is that they jump, so that they jump from different states. They don't exist in a state. They can jump from different states, and the different in either excitation or relaxation causes. So we'll talk about excitation as increasing energy, relaxation is lower, or sometimes called de-excitation. So here are the Bohr model shown, and I also combine it with the Rydberg constants, going from n equals 2 to n equals 3, for instance, will cause, I'm sorry, n equals 3 relaxing down n equals 2 releases a red photon, n equals 4 to n equals 2 that releases a green photon, and n equals 5 to n equals 2 that produces a violet photon. This is also known as the Balmer series. So if you want more history. So de Broglie, that's another scientist, came along. So de Broglie came along and said that particles could have wave-like character. And he came up with the idea of of course, the de Broglie wavelength. The Broglie wavelength is Planck's constant over the momentum. So momentum is mass times velocity. So the wavelength of a particle is equal to its momentum over, is equal to Planck's constant over its momentum. And so he could do this. He used electrons. You can shoot a beam of electrons, and you can form an interference pattern. And this shows electrons behave like waves. So you can get electrons to behave just like waves. Actually, you can have one electron. You can have an electron source. You can shoot one electron. An electron will actually interfere with itself. So that's one weird thing about electrons, that it will actually self-interfere with each other. So a single electron. And compares to a particle beam. So a particle beam, think of like a whole bunch of golf balls coming at 2 slits. You would get just 2 areas that they would go through. So, and where this is going to actually is that electrons will behave like particles or waves depending on how you look at them. If you want to behave like a particle, it'll behave like a particle. If you want to act like a wave, it'll act like a wave. So, but quantum mechanical theory is universal, so it applies to everything. So, according to this, a throw in baseball should exhibit wave-like properties. Why don't we observe the wave-like properties of a baseball? So remember the Broglie wavelength is Planck's constant over the momentum. And a baseball's large mass, its momentum is too big, and then because of that, its wavelength will be too small to observe. So that's answer A. And so the other question is, is the wavelength could it even be within the quantization of the universe? So remember, universe is space-time is quanta as well, so it has structure. And so does it fit within that as well? So that's a question I've always had about some of these things. Of course, we can't really directly probe the space-time quantization. So because we're in the universe. Also, so complementary particles or complementary properties. So you can't do both. You can't observe. So wave nature and particle nature, these have 2 different effects, and Because of this, since electrons can behave like either one, this is a problem, because then once we know about its particle behavior, we can't probe its wave behavior, and if we look at its wave behavior, it's not going to act like a particle. So because of this, there's an uncertainty. There's uncertainty in things, and the uncertainty principle state. This is Heisenberg's uncertainty principle. We can only know so much about an electron, as far as its position and its momentum. So velocity times mass is momentum. So if we know its position really well, we have no idea the momentum where it's going. And if we know where it's going, its momentum, we have no idea where the electron is. And there's a joke saying like Heisenberg was pulled over by a police officer speeding, and the officer says, "Professor Heisenberg, do you have any idea how fast you were going?" And he replies, "I know where I'm at," implying that he doesn't know how fast he was going. Like, ha ha, yes. So chemistry humor and physics humor is pretty tough, right? So, which tells you, and those are extreme examples where we look at things and find out its position and momentum very exactly. Most of the time, we just kind of know it in a general idea. It's kind of fuzzy, and because of that, electrons they're depending on the way that the state that they're in, they look and behave differently. So an electron is going to look and behave differently in a p orbital than it is in an s orbital or in a particle accelerator. In a particle accelerator, it's moving very, very fast, and as it's doing that, the electrons actually become very thin. They're almost like pancakes, and they tend not to repel, and you can stack them almost on top of each other in a particle accelerator. So that's kind of an extreme case for electrons. And so if you have an electron source now, and you say, all right, well, I want to see this electron in two different places at once, so I'm going to shine a laser on it, and when the laser hits the electron, it's going to flash. And so I'm going to start shooting electrons at this, and you know what? Electrons start to behave like particles. So if I took the laser away, it'll act like a wave. So that's interesting. Interesting about electrons. Which statement best summarizes the uncertainty principle? Both the position and the velocity of the electron can be accurately known in the same instant. No, that's wrong. Either the position of the velocity of the electron can be accurate in the same instant. It's closer that neither the position nor the velocity of the electron can be accurately known in the same instant. Well, this is a little fuzzier. I mean, it's kind of like, it's usually you kind of know things to a certain degree. Of these, the most accurate one is B. Because you can tell very well the velocity or its momentum. I'm sorry, velocity or its position. So, and well, yeah, it's more. We have no idea what's going on. Or at least we know it to a certain degree what's going on. So, and because of this, as I mentioned before, we used to believe in determinacy, like we can predict everything. I know exactly what's going to happen in the stock market, kind of thing. I knew I should have bought a bunch of Apple and Amazon stock. No, it's like we can't tell the future to a certain predictable amount. And the indeterminacy, I mean, there's certain things that we can kind of say, it's likely this is going to happen, but we can't really predict things. So it's more probability and statistical. So let's talk about classical trajectory. So imagine you're shooting hitting a baseball in a field, and that's gonna have a baseball. You're kind of its position, its velocity pretty well. Where an electron, you're shooting a quantum mechanical baseball, electron sized baseball, and there's going to be uncertainty position in the momentum, and then because of that, it's kind of not really known. But we know it's going to generally go in a certain direction, but we don't know exactly where it's at and where it's going. Same idea with a strike zone. So imagine like a baseball, it's always going to have be in a very classical location. Whereas an electron, you could shoot a single electron. Electron's going to have a certain density around an area, and it's going to have diffuse area around a much bigger area. So that's kind of what we're building up there towards is the wave function of an electron, what it looks like. And electrons have pretty big wave functions. More massive particles like protons and neutrons have much smaller wave functions, at least as far as the size of it. So, and this is just energy. Kinetic energy is 1/2 mv squared. M is mass, v is velocity. That's just from physics. And so the with an electron with a given energy, the best we can do is tell where it's at. And but the energy, but we only know to a certain degree. And many properties of the atoms, these are related to the energy of the electrons, and from that we're going to find them in various areas of the atom. And Schrodinger came along, and he came up with his wave equation. He has an interesting life if you ever want to read about Schrodinger. And he also, I listened to him. He's been long gone, but I went to the Nobel Museum in Stockholm, Sweden, and they always give like they have recordings of the different Nobel laureates, and Schrodinger's voice. I just remember how electrifying his voice sounded. I really wish I could have met the guy. But he came up with the idea of the wave equation. So this is all kind of you can, if you keep on studying mathematics, I don't know, maybe you already know this level of mathematics, but the wave function, if you operate on the wave function, which is called the Hamiltonian operator, it produces, on the wave function, it produces the energy levels of that wave function. And operator, so like the plus sign is an operator. So if you have 2 plus 3, 2 plus 3, that tells you that I take the number 2 and I operate it on the number 3 to then add on to it, and then 2 plus operation on 3 makes the number 5. So that's the operator. In this case, the Hamiltonian, the H, this is the kinetic and potential energy of the electron. The kinetic and potential energy of the electron operates on the wave function, and then there's some linear algebra that's done, and then it releases the eigenvalues. The eigenvalues is the value of a matrix. The eigenvalues are the energy levels of the electron, and then it shoots back out the wave function again. So that is the math that's involved. You can learn about that in subsequent classes, and that's the Hamiltonian operator operating on the wave function to get the different energy levels. And this is the Schrodinger wave equation right there. And the solution to the Schrodinger wave equation, we'll go through this with a quantum mechanical model. And you might want to listen to this lecture a little bit and then come back to it and listen to it again. But we'll talk about the different types of quantum numbers. We'll start with the first quantum number, the principal quantum number. Principal quantum number n, then there's the angular momentum quantum number L, and then the magnetic quantum number m sub L. So the principal quantum number, this is it's any integer greater than or equal to 1. So it exists as 1, 2, 3, 4, 5 integer steps up into infinity. So and then with n being bound then by positive whole numbers. We'll talk about this more later, but the potential energy of an electron in an atom we say is negative. We say a free electron has 0 potential energy, but a bound electron has negative potential energy. And that's just to make it easier. So it's a relative scale, and we pick a free electron as a relative scale, and we go from there. And the bigger the value of n, the further away from the nucleus it is, so the larger the orbital. So this is using Bohr's model. And then this is the E sub n is that's the Rydberg constant, the minus 2.18 times 10 to the minus 18 joules. So that's the Rydberg constant from the Rydberg equation there. So this is the different values for the different principal quantum numbers and for the hydrogen atom. The energy y-axis, higher up it is, and then you have the different values for the quantum number there. So the angular momentum quantum number L, this is bound by integer values. From 0 to the principal quantum number n minus 1. So it's it's positive integers and 0. And then the each value of this L, we have a certain orbital. So actually the different letters, so S means sharp, P means principal, D is diffuse, F is fine. Those are actually old spectroscopy terms for lines and spectra, but the sharp lines came from s orbitals. The principal, the p orbitals are from principal. D are diffuse. F is fine. So we kind of kept those going forward. It's more of kind of like a historical hangover of sorts. But I'll show you pictures of these orbitals later. So L is 0 is an s orbital, L is 1, that's a p orbital, L is 2, that's a d orbital, and L is 3, that's an f orbital. So what are the what values of L possible for n equals 3? It's going to be, it's 0 through n minus 1, so it's 0, 1, and 2. So, and that's C. So M sub L is bound by L, and these are integer steps from minus L to plus L. So let's say that L is 0, M sub L has to be 0. Let's say L is 1, that means M sub L can be minus 1, 0, and 1. If L is 2, M sub L can be minus 2, minus 1, 0, 1, and 2. So those are different values for L. I'm sorry, M sub L. Last quantum number is spin. This not really listed in the book. So electrons are particles known as fermions. Fermions are particles that have ratio of 2 integer spins that are not, then the ratio is not an integer itself, right? So 2 over 1 is a ratio, and I mean it's 2. But a half, that's a ratio of 2 integers. That's not an integer itself. So that's what I mean by that. And particles that have integer spins, those are known as bosons. And so what with this is fermions, by something later on called the Pauli exclusion principle. You cannot have 2 sets of fermions that have the same. You can in the same atom you cannot have 2 fermions with the same set of quantum numbers, and that's what gives matter its structure. Bosons, on the other hand, they can have the same set of quantum numbers, and light, energy are bosons. So you can put all the light energy as you want into a single point in space. Whereas electrons, you can only put 2 because you have one spin up and one spin down. So we'll talk about that later. But that's from the Pauli exclusion principle. And then when you're like, well, what is the spin? The spin is the projection of the magnetic moment of a particle or whatever it is you're looking at a given time. So an electron has a magnetic field and it's shooting in all different directions, but any given moment it has a certain direction to it, and that direction is the spin. So also the handedness of the spin. So matter, we give it the right-handed spin. Antimatter has the opposite handedness of spin. So that's more if you haven't learned about the handedness of things, that comes later in math classes. But I'm trying to inspire you to study things deeper. So I always thought this stuff was really cool. So hopefully, I know that I'm going outside the book for this in this lecture, but I'm hoping to inspire you to learn more math and learn more science. So describing the orbital, so a set of n, the principal quantum number, L, the magnetic quantum, L, the angular momentum quantum number, and M sub L, the magnetic quantum number, these describe an orbital. And this is a quantum mechanical model orbital, not the Bohr model orbital. So the n are the principal energy levels. These are also the rows on the periodic table. We're also going to build up to that. and the different values of N and L, these are said to be a sublevel or subshell. And so, for instance, n equals 3, the sublevels are, so, well, n equals 1, let's start at the bottom. N equals 1, L has to be 0. N equals 2, L can be 0, L can be 1. And then if L is 0, there can only be M sub L be 0. If L is 1, M sub L can be minus 1, 0, or 1. Same thing for N equals 3, but there can be L is 2. That means M sub L could be minus 2, minus 1, 0, 1, and 2. So, and so on. And summarizing this, the number of sublevels at any level is equal to n, the principal quantum number. So n is 1 is only of one sublevel. N is 2 has 2 sublevels. N equals 3 has 3 sublevels. Number of orbitals in each sublevel is equal to 2. L, the angular momentum quantum number, plus 1. So that means that L equals 0. The S sublevel has 1 orbital for L, so has 3 orbitals, and so on. And the number of orbitals at any level is equal to the principal quantum number squared. So L has 1, N equals, N is for 2, it has 4, N equals 3 is 3 squared, 9, 4, would be 4 squared, 16, 5 squared would be 25, and so on. So we'll go back to the atomic spectrum. So the whole point of this is to explain things that are going on. When an electron is excited, so excitation, I'm in elevated energy, it goes up in energy, and I'm relaxed, I'm lowering my energy, so the energy of electron goes down. And so the excitation involves energies going in, the electrons going in higher levels, electronic levels, and then relaxation involves lowering. So when the relaxation, a photon is released with the difference in energy level. And to go to a higher energy, the electron has to absorb the energy equivalent to the different states, the ones that it's jumping to. And but generally speaking, electrons in high energy states are unstable and they want to go to lower energy states. So why is that? Well, electrons are like people. So if I told you I want you to spend the next 20 hours doing something, you're probably going to pick, I'm going to lie down and sleep, or I'm going to sit down and watch TV. You're not going to say, you know what, I'm gonna be doing bench presses for the next 20 hours. I mean, maybe someone would do that, but it takes energy. It's a high energy state to be able to do that. So same idea with electrons, they're going to do that. And why do they do that? Actually, it's because of entropy. If you're wondering why, it's because of entropy, because it's having that high energy state. It's better to have a bunch of lower energy states than have a single really high energy state. So that's just it's probability is what drives that. But okay, but if you don't have to worry about that per se, like I said, I'm trying to inspire you. You can just say, hey, generally speaking, things like to be low energy, just like people. We like to be low energy. So kind of like cats. Cats will run around like a bunch of hyper fuzzballs at various times, like at 4 o'clock in the morning, but generally speaking, they tend to like to be curled up in a ball sleeping. So same idea with electrons. You can excite them for a little bit. So here is the quantum leaps. So an electron is going to jump up in energy. As it goes up in energy, it's going to relax down, and it emits the energy difference in form of radiation. And the spectrum of the hydrogen atom. So these lines are calculated. They were predicted and they're calculated. And you can generate. There are only for electron energy state n, there's only n-1 energy states. Okay, yeah, that makes sense. So then the idea is if you jump it up to level 3, it can only go to 2 or 1. So that means there's only 2 wavelengths that can jump off of this. So, and these are predicted by both models. And this intimidating looking equation here, this is just saying that the energy of the photon coming up is final state, 1 over the final n quantum number squared minus the initial squared. So, and then times that whole quantity times the Rydberg constant there. So if my final state is to the 1 and my initial state is 3, that's 1 over 1 squared minus 1 over 3 squared. It's 1 over 1 minus 1 over 9th, 1/9, and so 1 is 9/9. So 9/9 minus 1/9 is 8/9. So the energy coming from the n equals 3 state to the n equals 1 state, that's going to be 8/9 times the Rydberg constant there. So, it already gives you the answer. Which transition has the shortest wavelength? So, actually, no, the shortest wavelength is going to be also the highest energy. So, the lower, so these all go down by 1, but the biggest jumps are the lower. So, actually, the answer to this one, I guess it changed a little bit in the slide. The answer is C. So, because, and the answer is because of that, because of the n squared. So, you have 5 to 4. So you have 1 over 5, so I guess a final, 1 over 4 squared minus 1 over 5 squared versus 1 over 3 squared minus 1 over 4 squared, or 1 over 2 squared minus 1 over 3 squared. The biggest number there is the 1/4 minus 1/9. So that's the biggest number, looking at that. Okay, so here shows another picture of the spectra coming from hydrogen. And I mean, if you want to look up some ancient history, the light going to the n equals 1 lines, that's known as the Lyman series, and the visible wavelength, these are known as the Balmer series. So if you ever see those terms, that's what they mean. And of course, we as humans, we only see the visible light, so we see those transitions there. There's also infrared. I know I told you infrared causes vibration. Infrared can also cause energy transitions, electron energy transitions. I mean, things can do more than one. Like radiation can have more than one effect, and depending on the circumstances. So infrared, especially near infrared, closer to red light, can have energy transition states there, electron energy transition states. And okay, so let's then talk about the density probability for the orbitals. And so I told you can only see electrons and we can know its position and momentum to a certain state, or to a certain degree. So if you look at an s orbital and you look at the probability density of that, so looking at this part B, the y-axis, the probability distance, probability density times or versus the radius from the nucleus, and you can see that it has an asymptote close to 0. Then besides that, what is this psi squared? It's not really explained all that well. What you do is you integrate the wave function vector dotted with its complex conjugate, and you do that over all space. So I know I'm probably making you more confused by that, but if you do that math operation on it, it gives you the psi squared, the probability density. That's another fine point of this. And I encourage you to study more math and study future classes. So what? Well, let's apply a different model. Let's talk about the onions. Onions are they're layered. They're like ogres, if you like Shrek. They're layered. If you kind of apply the onion model to that, and you look at shells coming off, you get a different picture. We'll talk about that soon. But the s orbital has kind of a spherical looking thing, and the number of nodes. A node is an area of 0 electron density, and the 1s actually has no node. So the 1s has no node. Then you apply the onion model. Look at the shells coming off, and the probability coming out of the 1s electron, and you get a maximum. And the maximum there is 52.9 picometers. And so there's a couple things. The other thing to notice, you can see that there is, like, at zero, actually a little bit past zero, there actually is some electron density. And you probably were taught that electrons are not the nucleus of the atom. And it turns out that electrons can be and are in the nucleus of an atom. Of course, the nucleus of an atom is not very big, but the electron does have some of its density inside the nucleus of the atom, especially the 1s orbital. You can make atoms atoms like using other particles other than electrons. You can make them from muons, for instance, and muons are much more massive. Therefore, there's much more interaction with the nucleus of an atom. But the nucleus tends not to have that much of effect on the electrons. I mean, other than the force, the electrostatic force, the positive and negative attraction, but the different isotopes, so different number of protons, different number of neutrons, the different isotopes tend not to have much of an effect on the electronic structure of an atom. But it actually does. It has a small effect. It's measurable, but it's really hard to find. So actually, different isotopes will change the electron structure of an atom, but this is most commonly seen in the 1s orbital, because that is the orbital that has the most density in the nucleus of an atom. Okay, so we mentioned the 1s orbital has no nodes. The 2s orbital actually has a node. You can see the bottom is the onion model, the total radial probability, and you have a small peak, and then you have a longer peak later on. And actually that small peak, that's something later on we call it penetration. That's important for a concept called shielding. The idea is that certain electrons are shielded by the core electrons shield the outer electrons. But because the 2s orbital has that little bit, it's called penetration, goes into that, the shielding is not as pronounced. So that's one of the things with the shielding we'll talk about later on. And similarly, the 3s orbital has 2 nodes, and it has some of that area inside, but it still has a maximum. And where is the electron, you ask? Where is it? It's in all these places at the same time. So electrons are not like classical particles like baseballs. They are in all these places at the same time, and we know its position-ish to a certain degree. It's not like it's moving around and switching back and forth. It's actually occupying all this space at once. At least the force of the electron, the magnetic and electronic field of the electron, is occupying this area there now. We're not so sure about the mass. I mean, that's one thing about I mean, we can measure mass by gravity kind of thing, but it's hard to really kind of pinpoint the mass of things. So radial distribution function. So we already mentioned the psi squared for the probability density, and the nodes. The nodes is where the probability drops to 0, and this is going to be more of the wave-like behavior of things. So, and really, what this slide I've already mentioned in the lecture so far. Let's talk about the p orbitals. So the 2p's. So we'll start with the two p's, and well, they say there are 3 lobes. They're not. The p sometimes says perpendicular. It really means principal. But these are the lowest energy of the s orbitals, and then second lowest are the p orbitals, and then they tend to shoot off in one direction. So here are the 2p's, and here's the radial distribution. For the 2p's, there actually is a node at 0. So the origin has a node, and the p orbitals, they tend not to have much density inside the nucleus of the atom. So therefore, the nucleus, the different isotopes don't affect the p orbitals as much. But there it is, and they're just perpendicular just by the 3 different Cartesian coordinates, x, y, and z. And the m sub l, they just orient themselves different to the different Cartesian axes. And the d orbitals, there's 4 There's 5 d orbitals for each, and we'll talk about the 3Ds mostly. So there's the dxy, dyz, dxz. These all look like clover leaves. The dx squared minus the y squared, and then along the z-axis, or z-axis if you are, not from the United States, is along is a kind of it's a goofy looking one. It's like a donut with 2 lobes. So let me show you the pictures. So here are the dxy, the dyz, dxy, dxz. These all look like kind of like clovers in different orientation. The dx squared minus y squared, these are going to be along the Cartesian axes. And this is going to be important for bonding. And then you have the dz squared orbital, it's along the z-axis. And we'll talk about these in subsequent chapters or subsequent courses if you study further along. And I wanted to bring up an advanced topic again, just so you can get your money's worth from this lecture. There's something called the Jahn-Teller effect, and it deals with many copper compounds, for instance, and it has to do with axial distortion. And it actually comes directly from this dz squared orbital, where the an octahedra is kind of elongated. And so actually, because of the shape of that dz squared orbital, we see a certain break and change in the symmetry, well, elongation of the molecules that are formed because of this orbital. So I mean, this looks like imaginary stuff. There actually is some measurable and observable things from these shapes of the orbitals. So, but we'll talk about this later on in other chapters and in depending on how far you get on this book or coursework. But I always thought this stuff was really interesting. So the f orbitals, similar. There are 7 f orbitals from the different values of m sub l, and these have funkier shapes. So you can see they're kind of, some of them are like the dz squared, and some of them are like and then they're within the kind of interplanar ones with the 3Ds. So these are the 4Fs orbitals. So those are interesting looking. And with the phase, this is going to come in important later when we talk about molecular orbital theory. So, well, we'll start off with the S. S is always positive, but the P's, the P in various ones, they have there's a plus and minus phase, and they cross where there's a node, and we will talk about this in other sections. But an s orbital, for instance, is actually all positive. A p orbital with although the 1s orbital has no node, but the p orbital has a node and it has a positive negative sign. This is important when it comes to, because we can model the orbitals in terms of interference and how they bond. So this is going to become important later when we talk about bonding and interference. And why are atoms spherical? Well, if you look at, this is like, if you see, you have the P's, the D's, and the S's. So the P's are in yellow. If you can see the yellow, I'm sorry, the D's are in yellow, the P's are in red, and the S is in blue. And you can see that they all kind of, it's kind of not a very even thing, but if you look far away, it's more or less spherical. So the force field, at least the electronic and magnetic field coming from an atom, is mostly kind of spherical in shape. So that's the idea. Why are atoms spherical? That's because of those different orbitals, and they all come together, and they kind of at least force-wise look that way. So hopefully I've inspired you a little bit, that I've been inspiring you, and I hope to continue inspiring you next chapter. Thank you for listening.